Perfect. Hello, everyone. Good afternoon. Nice to see you there. I'm really pleased to welcome you for this online technology meeting on Metasurfaces. So I'm Jeremy Picot-Clement. I'm technology expert at EPIC. And before to start, I will just give you a few words about EPIC. So EPIC is the largest industrial network in the world in the field of photonics. So with today more than 800 members covering all the value chain of the photonics industry, from the component manufacturer to the design and prototyping company, to the end user and system integrators. We also cover all photonics application, which is wide from space and defense to biomedical and quantum, including AR, VR, of course, agriculture, PICs and laser technologies. Our aim is to create a sustainable European photonics industry, and how we offer a large panel of services to members. We offer technology support, market and technology report access, networking event, access to market, US, Asia, mentorship, HR support with the website Jobs in Photonics, and also investment support. Here is the EPIC team. So we are now 12 people, all passionate by photonics in 3 different teams. So I'm a part of the technology team with my colleague Ivan Nikitsky and Antonio Castello. And then we have the marketing team with Anna Martinsen, Anna Traktova, and Elisanda Lara. And then the event management team with Neringa, Natasha, Martin, and also Lydia, who is in charge of the program. A few words about the next event we will organize at EPIC. So we organize a lot of events all along the year on all different topics. Talking about photonics, of course. So physical meetings in 2025. So we'll be at APE, where we'll organize a Tech Watch. We'll have also a nice meeting on photonics integrated circuits at Legentech in Switzerland. We'll be at the W3 fair in Wetzlar, Germany. And then end of March, we'll organize the annual general meeting in Barcelona, Spain. We'll be also at OFC, where we will organize, members lunch, VIP networking, members one as well. And we'll organize also a nice event beginning of April at Thales, talking about innovative and disruptive optics. And about online meetings. So here is the same. We organize, online technology meetings. So the next one will be next Monday on geological and mining application. We'll have also an interesting online meeting talking about market reports on metamaterials and metasurfaces for optics and RF by Thematis, beginning of April. And then we'll have something on laser processes for automotive. We'll also organize something on marketing, like basics for marketing for exhibition and print materials. We'll have also an EPIC member new product release at the end of April. And beginning of May, we'll have something on new developments for microscopy and bioimaging. We, of course, invite you to check our website, where you could access to all of our events all along the year. A few words also about the value chain we have today. So all these companies are meeting today. So as you can see, we cover all the photonic value chain, from the equipment manufacturers, consultancy company, component and module companies, software and design, to the end users and system integrators, service providers, including also a lot of research and development centers. If you want to be in contact with one of these companies, feel free to contact me, after the meeting, and we'll be really pleased to do this for you. And here is the agenda of today's event. So we have 7 speakers for today. We'll start with Axel Clouet from Yole Group. He will talk about a brief overview of the optical metasurfaces industry. Then Badri Karzabi from Solnil, Inorganic resins for the fabrication of optical metasurfaces. We'll continue with Theodore Nielsen, CEO at Nil Technology. We'll talk about meta-optics manufacturing and optics solutions. Then Timo Skalos from Iron Delta Tech, industrial application of optical metasurfaces. Then we'll continue with Daniel Pereira from Buller. You will talk about optical coating on thin glass, enabling manufacturing of metastructures. Then Lieven Pennick with Planopsim, Metalenses design software. And we will end this meeting with Matthew George from Moxtech, and you will talk, Matthew, about progress in commercializing visible wavelength metalenses. So thank you very much for all of the attendees today, all the speakers. If you have any question, we'll keep some times after each of the presentation, 3, 4, 5 minutes to discuss and to ask to take your question for the speaker. So feel free to do it. It's an open discussion. And yeah, thank you very much again, and let's welcome our first speaker, Axel Clouet. So you are a senior technology and market analyst at your group, and you will talk about a brief overview, and you will give a brief overview of the optical metasurfaces industry. So Axel, you can share and start your presentation.
Okay, so can you hear me well?
Yes.
Okay. Can you see my screen?
No.
Okay. Okay, here we are.
Good. Perfect.
So now you see my screen, right?
Yes, you can start.
Okay, so hello everybody. So my goal today is to give a brief overview of the optical metasurfaces industry. So I'm part of your group. So your group is a market intelligence company mostly who provides market intelligence and teardown analysis for the semiconductor industry. So basically, these are our main two activities: market intelligence, teardown, and reverse costing. Most of the information that I relate in this presentation come from two reports that we wrote last year: Optical Metasurfaces 2024 and Displays and Optics for X-Reality 2024. Okay, so here is a simplified definition and applications of the metasurfaces that we consider in YOL. So basically, we consider that metasurface component is a diffractive optical element, which critical pattern size of the diffractive structure is in the range of the operating wavelengths. So basically, two categories of components. On one hand, the gratings, binary, slanted, blazed, and let's say this kind of nanopillar-based diffractive optics. So these gratings, we'll find them mainly in augmented reality glasses, or there are some concepts related to 3D naked eye display. And this nanopillar-based diffractive optics mostly in the world of imaging in a 3D sensing module as well as camera modules. Okay, so here is an overview for the display. So in the blue bubble, you have the representation of the optical functionality that is achieved by such components. So basically for the augmented reality, what we look for is the optical coupling. So bringing the light from the free space to a waveguide and outcoupling the light from the waveguide to the free space. So here is so the goal of that is to bring the light from the micro display engine to the user's eye. So this is the case. Most of the AR glasses that are presented at the moment use this kind of diffractive gratings. This is the case, for example, of the Orion Meta prototype, which is based on silicon carbide waveguide and gratings. The other applications where we can find this type of structure could be what we call the 3D naked eye display. It's mostly related to the activity of Leia, so it's a company who works in the display activity. So the goal here is to integrate micro optics in front of the pixels to enable 3D imaging without wearing any glasses or any devices. So here there are two approaches, a refractive one or a diffractive one. So the diffractive approach is a long-term perspective, but still enable interesting things like 2D and 3D switching mode. For the imaging world, so basically the metasurfaces can be considered as a standalone component into the camera module to replicate what does a standard refractive lens. So basically the focus or the collimation. It can also replace more traditional diffractive optics by doing what we call a pattern projection. This is what is used in biometry module, for example. So in that case, the metasurface allows for size reduction of the camera module by removing several optical elements by one single metasurface, replacing them by one single metasurface. So the main goal is to reduce the size of the module as well as the cost. Here is a brief timeline of what we observed linked to this type of metasurface. So we saw them for the first time in 2023 into this module from STMicroelectronics in their smartphones. So it was at the rear side of the smartphone in what we call a DTOF multi-zone array for range detection. In 2024, we saw for the first time this type of metasurfaces going into the Face ID illuminator module of the iPad Pro M4. Now we expect this type of metasurface also to be integrated in the same way as in the iPad, but for smartphones biometrics. And so until now, we see most of these metasurfaces operate at single wavelengths for near-infrared imaging, and before seeing them operating in RGB for color imaging, so where we can find most of the volumes of camera modules, we should probably wait longer because there are still some technical challenges to solve. And I'm glad we have a presentation about this topic later. So here is what we found in this in our laboratory in your group. So we do the teardown of the modules. So here, basically, on the left-hand side, you have a comparison of the structure of the Face ID module found in the iPhone 14 that didn't use the metasurface. So we see we have 3 refractive lenses on the illuminator, plus what we call a DOE, so a diffractive optical element. And you see that the diffractive optical element is made of 2 substrates with linear patterns here that make the diffraction, and at the end allows for a dot pattern projection onto the user's face. And now in the iPad Face ID module, the last one. So here there is a cross section of the module. You see that in front of the illuminator there is only one single element, and actually when we perform SEM image, we see that it's a nanopillar shaped element, so a metasurface. So we'll do a report comparing the structures of this module in terms of pure architecture and cost, so stay tuned to our activity. The other concept where we can find metasurfaces is when we use them as a deflector. So it can be used as a spectral deflector or as a polarization deflector. In that case, the metasurface is directly integrated onto the pixels of an image sensor, for example. So it replaces the micro lenses, or it can be complementary. And the main goal, the main added value of such concepts is to increase the signal-to-noise ratio that is collected by at the pixel level. So here, for example, there is Samsung that works on what they call the color router to increase the signal-to-noise ratio in RGB image sensors. There is also this startup AO that has been spun out few times ago, also working on a kind of color routing like this. And there is Metalens that released a concept of polarization sorting. So it's something similar but related to the polarization state. And here the goal is to enable biometrics, not doing 3D but polarization sensing. Okay, so here is a brief quantification. So basically, the goal of our report last year was to try to understand where the metasurface could fit with what application, and what could be the market associated to the business of metasurfaces. So we counted in 2023, the market could have represented $62 million and could go towards $2 billion in 2029. And you see that when we analyze the split between imaging and display, most of the part of this value is in the AR field, so the display side. So the business opportunity is significant, but this is pretty uncertain because it's totally linked to the emergence of the AR market. For the imaging, it's so the business opportunity might look smaller. However, we are pretty sure that metasurfaces will eventually penetrate at least the near-infrared imaging modality. So we are pretty confident that this scenario will eventually occur. Here is a brief overview of the different design, manufacturing, or materials that can be used for the manufacturing of the metasurfaces. So basically, at the display side, so we have so what we'll use in the AR eyepieces will be the gratings. So the gratings have a relatively uniform shape over their size, let's say. The critical pattern size is not so small compared to the imaging optical functionalities. And also the refractive index can be smaller compared to what we need in the imaging field. So the candidate, let's say the process that is anticipated to serve the AR market is based on what we call the nano-imprint lithography. So this consists in, for example, we can imagine we have a substrate, we deposit high refractive index polymer resist, and we directly imprint the structures with a stamp on it. For the imaging side, so the design is much more complex. The refractive index needs to be higher. So currently, what has been spotted in our teardown, let's say, is mostly using a standard semiconductor process, so silicon and silicon dioxide process. So this is suitable for the near-infrared wavelengths, but if we want to move to the RGB domain, so the visible one, we'll probably need to find new solutions based on glass substrates and titanium dioxide, for example, with additional challenges also linked to the process engineering. Here is a brief overview of the supply chain, how it's structured, let's say. So here is a representation of the supply chain. And in the green area, this is where we find most of the startups. So most of the startups are focusing on, so there are some that focus on the, let's say, they are fabless designers. So they bring the technology from the knowledge in the laboratory to the industry. Some others are really active in the material development. There are a lot of challenges, especially around the nano-imprint lithography, to find some materials that can be easily imprinted with good properties. And a lot of startups also try to have a central position with a more vertical business model and position themselves as a manufacturing platform to provide a one-stop service to the industry. So this position is quite attractive at the moment. Here are some recent news to show that the metasurface is a very active domain. So there is the acquisition of NILTI by Radiant Optoelectronics. So it has been announced a few months ago and eventually validated few weeks ago. There is also this investment in Lumotive. So the company raised $45 million. So this company works on active metasurfaces to perform beam steering. So the idea is to, for example, to perform a LiDAR beam steering without any mechanical moving parts. And it starts to work actually. And there is also the company related to the AR eyepieces, Celid, who raised $13 million a few weeks ago. Thanks for your attention. That's all for me. I hope this is a good introduction to the topic, and now I will take your question or let the next speakers present their work. Thank you very much.
Thank you, Axel, for this nice overview. So we have already a question from Thomas Aklichtner. So Thomas, if you want to ask a question.
Yes, I can ask also directly. So I have the question. So do you see also Metalens made of silicon carbide in the future, for example?
Silicon carbide. So we believe now it's mostly, so it has been demonstrated, let's say, in the Orion prototype, but it's still very expensive. So we don't think that will be the final solution to address the mass market, let's say. So probably for some range of products in the very high end, very expensive product, it could fit, but probably not for the mass consumer market, let's say, for the volumes. For
okay,
the,
thanks.
well, yeah, sorry.
Yes, Thomas, you have another question? All good? Okay, so let's move our next question. Jorge from HEF. You are muted, Jorge. Jorge, you are muted.
Hello? Okay,
Yes.
sorry, excuse me. Thank you. My question related is about photolithography processes for augmented reality one concerning plastics.
Okay.
Any plastics is a general, very general concept. Any particular plastics you envisage that will be most concerned?
Yeah, I'm sorry, I don't have the technical expertise to answer this question. So, so I should refer to my colleagues. So maybe we can let's say continue by email if you want.
Okay,
Yeah.
thank you.
Yeah.
Thank you, Jorge. I think you will have the opportunity to ask a question to one of our next speaker anyway.
Okay, thank
Yeah.
you.
Yes. Another question. Sorry for the name. From the Furtwangen University, Hakan Alaboz. Please, Hakan.
Can you hear me?
Yes.
Okay. My question is, what is the dominant application frequency in this metamaterial market?
Okay. Yes. So basically here, sorry, when we talk about imaging, we mean mostly 3D sensing for biometrics, because this is where we think that metasurface will penetrate first. When we talk about standalone metasurfaces. So in that case, it's 940 nanometer mostly. Yeah, so basically this is the idea here. So in 3D sensing, we find 905 nanometer, 905, 940. Then there are some tentatives to move to the shortwave infrared, but it's more niche, let's say, except in the automotive LiDAR. And for the imaging, so for example, if we look at this concept, so this is for the RGB band, but the optical functionalities is not focus, or it's not collimate, so it's something different. It's a deflector, so it's a big. So in that case, it will be a broadband. But for focus, collimate, and collimation and pattern projection, we think it's 940 nanometer mostly.
Okay, thank you very much. Yeah.
Thank you, Hakan. So a question, and we had another question from the spectator. So Rajit, you had a question? No, not anymore. Okay, so thank you very much, Axel, again.
Thank you.
Nice presentation. Thank you a lot. And now let's move on with our next speaker. We welcome Badre Kerzabi. So Badre, you are a co-founder at Solnil, and you will talk about inorganic resins for the fabrication of optical metasurfaces. So, oh, sorry. We have maybe a last question for you, Axel, from Focus
Okay.
Light. Do you want
I'm still
ask
here.
a question?
Hello, thank you. Very interesting overview. There's always a discussion if a diffractive grating is a metasurface or not. So you included those in your report. I know this topic, we have the same internally. So I actually wanted to know, did you look at the efficiencies of the different devices that are already on the market? Because this is the other point always. So I mean, for metasurface to compete with classical or more refractive optics based systems, the efficiency has to be comparable, I think.
Yes, you mean the efficiency for the AR gratings. So
well, either the gratings or for imaging or for either way.
For the imaging, we didn't compare. For the display, it's more my colleagues again. But I guess that it's in the range of 1% efficiency, something like this. So there is a lot of light that is still waste.
Okay.
I'm afraid I'm saying some mistakes, so need to check later. But yeah, this is something we look at. Maybe I'm not the best person to answer this question right now.
Thank you very much. No worries.
We can follow up.
Thank you, Wilfried. And a last short question from Ranjit Kumar. Please, Ranjit. You can ask a question, huh? But you are muted. Ranjit.
Okay.
Good. We can hear you.
Right. Okay. So can you share your thoughts about the role of the metasurfaces in analog optical computing?
Sorry, can you repeat, please?
role of metasurfaces in analog optical computing?
For analog optical computing.
Yes.
Yeah, so this is something that we didn't explore yet because we covered mostly what is driving the market takeoff at the moment, so imaging and display. But this is something that we see there is a traction, and especially so there are some startups emerging for so it's not optical computing, it's more like analog image processing. But also in the field of optical computing, we have so this is something that we need to dig in our further updates of the report.
Right.
Yeah.
Thank you.
Thank you, Ranjit, and thank you again, Axel. Thank you.
Thank you.
And yes, sorry, Badre. So it's your turn. So Badre Kerzabi, co-founder at Solnil. So Badre, please.
Okay, perfect. So thank you for this invitation and for this opportunity to present you the work of Solnil. So I will go through the inorganic material we developed for fabrication of optical metasurfaces. So first, a few words about Solnil. So we're a startup. We started in 2020. 12 today, and our main focus is really to develop material and processes for micro fabrication, mainly for optical applications such as augmented reality, laser optics, and optical metasurfaces. So I've been fortunate to have the support of various French agencies like BPI, DGA, and more recently we got a grant from the EU, the EIC transition, that allow us to upscale our pilot line from 2-inch 50 millimeter to 8-inch as ongoing. So what are the materials that we are developing at Solnil? So what we developed is a soil gel chemistry that allow us to deposit a wide range of metal oxides, silica, titanium mainly, using simple liquid deposition processes, such as spin coating, deep coating, and spray coating. And using these simple processes, we can deposit high quality optical coatings, which have also the benefits of being compatible with nanoimprint lithography. So it could be both used to make optical coatings or nanostructured surfaces. Since our materials are purely inorganic, they have the advantage of being highly stable with temperature, UV, or mechanical stress. They can also withstand high humidity. And one of the distinctive features of what we do is the control of refractive index. So we can go to very low refractive index from 1.11 up to 2.6 for visible light, which is quite unique. Regarding the process options, so our main focus today is nanoimprint lithography. This is what we developed for augmented reality applications, where you need to make these slanted gratings or binary gratings, like you all showed earlier. And it's suitable, direct nanoimprint is suitable for aspect ratio up to 4:1. When you go to more challenging aspect ratio, although you see some publications about direct nanoimprint of high aspect ratio, I think the easiest way and what most of the industry is doing today is to use traditional top-down etching approaches, which are used today in the semicon industry or with microelectronics. And what we propose there is just to replace atomic layer deposition or PCVD by a coating made by spin coating to reduce the cycle time. And then you can use your standard process based on nanoimprint lithography or deep UV to etch this layer. So now if we come back to the refractive index range that we can cover, why is it important to have such a refractive index contrast? Usually when you work on a metasurface, the base building component is what we call a meta-atom. So you have these pillars usually of high refractive index materials, and you play on the dimension to have a full coverage of the phase, develop your metasurface. And usually for integration into a product, you need some kind of encapsulation layer to protect this metasurface from mechanical damages and to have better integration into your product. And what is important there is the refractive index contrast of this encapsulation layer with the metasurface. So if we take an example, and it was done with the help of PlanOpSim for the simulation. If you want to make let's say a design for visible light at 520 nanometer, if you use a material with a refractive index of 2.3 and encapsulation layer of 1.5, you end up with having to etch pillars with a height of 1.2 micron. On the other hand, if you can increase the refractive index contrast, so if you can go to a refractive index of 2.5 for the metasurface, and to reduce the refractive index of the encapsulation to 1.12, now you need only 600 nanometer pillars height. So it has a kind of huge impact on the processing. So using this wide range of refractive index allows you to simplify your process. So now, how did we achieve such high and low refractive index? So the high refractive index, we obtain it using kind of specific TiO2 formulation. So we start not with nanoparticles, it's something smaller. We start with molecular precursors, and we have building blocks which are quite specific. They have a kind of hard core and kind of soft shell. So when you deposit this material by spin coating on a layer, and when you have this drying, the soft shell tend to merge, and basically what you end up, you end up with a very compact and dense layer, which allow us to get this very high refractive index. And as you can see, we managed to have very small crystal grains, which is why we managed to obtain, even for very high refractive index, this very low scattering or absorption. So here's some kind of SEM pictures of gratings we obtained with our process. On the left is kind of standard salt gel, which is not controlled. If you don't control the crystallization, you end up with very big crystals, like you see on the left, which will cause a lot of scattering and loss. What we achieve at Soil is that we managed to keep and to control this crystal growth to have kind of very dense layer with no scattering by keeping the crystals below 6 nanometer. This is the key to achieve a refractive index and optical quality. For the low refractive index, the approach is quite different. So what we start with a silica formulation. So we have a formulation that can, after curing, become pure glass. And what we did is that we managed to control the porosity of this layer. So we managed to increase the porosity up to 75%, which allow us to reduce the refractive index down to 1.12. And to keep the optical quality and the clarity, what we need to do there is not to control the crystal size like we did for TiO2, is now to control the size of the pores. So we have very small pores below 10 nanometer, and this is why we have no scattering or absorption, because the pores are very small. Is a key. And so now, so far, what we've shown is that kind of standard approaches to make the metasurfaces. So basically, you start with a thick layer of the high refractiveness material, you etch it, and then you do the encapsulation. One of the challenges that a lot of customers today have with etching TiO2 is that it's kind of difficult material to etch. So they have to come up with very slow etching processes. Sometimes they use atomic layer etching, which is quite slow. So we have been working on another approach at Solnil, is that we went the other way around. So what we did first is, can we just, instead, because our materials are liquid, just make holes in silica, because silica is very easy to etch, especially porous silica. So you can very easily etch very deep grooves into silica. And then you keep using our material, which is liquid, we can fill the gaps. So this is what we have been working for the past year. And so it's a process that now is working well and running for small aspect ratio, with an aspect ratio of 1, and regular patterns. So now it's something that is scalable to large area. So basically, we just start with nano-imprinting a low refractive index material, and by using specific deposition parameters and specific chemistry, we managed to have only a kind of selective deposition in the holes. So today it's very efficient and it works quite well for standard patterns, uniform. And now we're in the process of developing this further for metasurfaces and more complex designs. And so, as conclusion, what we have been working at Solnil is really to extend the range of refractive index, to really simplify the fabrication process of optical metasurfaces. You can find more details on our website for each material. And today we will start maybe to provide, we're interested in partnering with end users or design companies who have some ideas about metasurfaces, who would like to work with us to show how our materials could enable their designs. And thank you.
Thank you, Badre. Thank you very much for this nice presentation. Question for Badre. You can raise your hand. Yes, Lieven, you can start.
Yes, thank you. I'm curious, in the sol gel process, do you experience any shrinkage during deposition, especially when you combine that with the imprint? And is there a way to account for it?
Yes, quite challenging. For direct on imprint, we have a significant shrinkage for the high reflection index material. So now what we are working on is to have some kind of guidelines to see first if this shrinkage is repeatable. And what we have seen so far is that it's very repeatable and predictable. So now is to have some kind of design guidelines to share with design companies to include that in the mold design. So the objective for us is to pre-compensate in the mold design.
Thank you. Another question from Elena Luxotica. Please, Elena.
Sorry, thank you for the interesting talk. My question is whether you have some solution for the big size of the fabrication files, that when you produce a big component and when you need to have a large GDS file for it, like, do you use any algorithms? Do you have
no, so far it's really our partners who do the designs or customers who handle that. On our side, we don't have such a solution.
Mm-hmm. Okay, thank you.
Mm-hmm.
Thank you, Elena. Any other question for Badre? Okay, so thank you, Badre. Thank you very much. And now we move on with our next speaker, Theodore Nielsen. Theodore, you are CEO at NIL Technology, and you will talk about meta optics manufacturing and optics solutions. So, hello, Theodore. Good afternoon, and please, the floor is yours. So yeah.
Can you hear me?
Yes, perfect.
And what can you see my slides?
Not in full screen. No.
Typical. Give me 1 second. Hang on. No. One should think that we had this under control by now.
That's a problem on the right.
I don't know. I have 3 screens here. I'm a mess.
Yeah.
Sorry
Okay.
for this. Give me 1 second. Now?
No.
I think it's okay, huh? You see it, huh?
Yeah, we can see it. You can go like this.
Let's just go with this. Okay, thank you. Sorry for this. Good afternoon, everyone. I will talk a little bit about meta optics manufacturing and full solutions by NIL. First, about a great talk. I agreed with everything you said. So good talk. First, a quick introduction to NIL. We are a little bit more than 70 employees. People. We are working mostly with the manufacturing of meta optics. But as our name indicates, in NIL Technology, we come from a background of nano-imprint lithography. And for many years, we also developed masters. And it's still a product line that we keep, especially for the AR. But I'm not going to talk so much about that today. We have a headquarters here in Copenhagen with R&D and also R&D and mastering in Sweden. We have process development in Switzerland, and we have built up a mass production facility in Malaysia and have people on the ground, mostly customer focused in North America. Everything we do with in-house equipment, so in-house clean rooms. We're having in-house e-beam nano-imprint etching and all the optical characterization equipment that we need to bring up manufacturing of meta optics. So I think that's the high level of NILD. And as Alex also mentioned here, early January, the big news for us is that we got acquired by Radiant Optoelectronics. They are a company who are focused on backlight units for displays. Back in 2023, they bought Nanocom, a Finnish company doing roll-to-roll nano imprint, and who are active in front light units for displays. So now NILD is part of a group with more than 20,000 employees. A lot of know-how and focus about manufacturing by replication, injection molding, nano imprint kind of technologies. So from a technological point of view, the synergies that we manufacture from making a master and somehow replicating this, of course, in very different settings, but there are still a lot of similarities. Any questions to this, I can always answer later on. All companies here in the group are focused on optics. I think I mentioned already, we do a lot of masters. That won't be the topic of today, but the majority of our development efforts and our investments goes into establish manufacturing of meta optics, and that's what I will talk about today. And I think in this crowd here, I don't have to explain what meta optics is. What we do is that we are bringing a full solution forward for the manufacturing. We can operate in what I would call a classical foundry model. We can take in designs from our customers, and then we can adapt them to our process. We can manufacture it, we will test it, and then ship out the optics. We can do dicing, we can ship out the wafers. I think it's up to our customers. But we also have the capacity and capabilities to take a larger responsibility. So taking in the optical specifications, and then we can and will design the meta optics to meet those specifications, and then we take it through the full loop again. And as you will see later, we have the technology available. We can even, and we are shipping actually cameras as test products right now, and those can be built with our in-house technologies. We are doing a great deal of prototyping. We do that by electron beam lithography and etching. It's a technology that's very natural for us. We've been doing this for the last 20 years. This is very similar as to making masters for nano imprint. And transferring the process to mass production, it's a very similar process to create the master. The GDS file is the same. It has the same file size to answer the questions from before. So we're building the master with e-beam and etch, and then we use the nano imprint in the lithography mode, as Barbara also pointed out. So we're using nano imprint in a lithography mode, and we use the imprinted pattern as an etch mask to etch the meta atoms out typically in amorphous silicon in case of a near infrared. Without going into too much details, but I have some data here. We are very often characterizing the optics by measuring the efficiency of the optics. And on the top plot, you see here how the efficiency changes as function of radius on the wafer, and we control the process very well. And in the lower graph, you see here how we have repeatability from wafer to wafer. Of course, this is very sparse data plots, but we have plenty of data to convince anyone about having a very reliable process for bringing up the meta optics for high volume. I think it's about a year ago, we made a publication about how we align our in-house design with our prototyping and our mass production capabilities. This is how we are setting up our process by understanding and controlling the design and making sure it fits with our process capabilities. So there's a reference here, and anyone interested, you can always just send me an email and I'll forward the paper. But basically what the graph here shows is that what we simulate from an efficiency point of view is just a simple focusing lens. is also what we build in prototyping using e-beam and etch, which is also what we build when we take it to nano imprint and the manufacturing. So we have a very, very good understanding about what we do, and it gives us a very high level of confidence that when we design, this is also what we build and what we will get out. Also, about a year ago, maybe a little bit longer, we saw that the meta optics industry was definitely not, it's maturing now, and I also see a lot of people in this call, but one of the challenges we faced from NILT was that people thought it was interesting to consider meta optics, but they didn't really see the use cases. They had some doubts that it could be taken beyond nice academic papers and for real use cases. And we took up the challenge and said, okay, why don't we build a camera? It's difficult. To build a camera is difficult, period. To build a camera purely based on diffractive optics, which I agree, Alex, it is very difficult. And so we came up with this, the Meta Eye. We built a small camera, focus distance of 15 millimeters. It consists of two metalenses stacked together on top of a sensor. There's no air gaps, reduction of anti-reflective coatings, and created a super compact camera. And you see here Wally on the screen, and then you can hardly see where the cameras are placed inside the frame as a demonstrator. The picture at the lower in the middle is the raw data coming directly from the sensor. And then we just launched the demonstrators a month ago, that we had reconfigured the camera and also demonstrated what we call the meta macro. This is a close-up picture. The grayscale picture is a close-up of a banknote where the camera is placed 2 millimeters from the surface. It images. And to the farthest right, you have the meta infinity, where we have made the focus distances at infinity for more gesture recognition type of applications. It's all based on the same camera architecture that is outlined here. No surfaces, no available surfaces. You just have two meta surfaces embedded in this cube, and it works very, very nicely. Let me see here. Also, a month ago, we also announced the first demonstrators between Trinamics, a company in the BASF group, BASF, and NILT, where we have built a behind-the-screen authenticity, face recognition and authenticity application based on algorithms that has by Trinamics that has been proven for banking systems, etc. In this case here, we have one piece of optics that has side-by-side diffuser and dot projector. So that's what you see here in the circled out. And this is a technology that Trinamics is now moving forward with, and we're quite excited about the results and the progress of this. And I think that more or less brings me to the end. What I really wanted to share with you, with everyone, NILT is a vertically integrated company, and I can understand from Alex that there are apparently many of us. We prototype by e-beam and etch. We mass produce by nano imprinted etch. And doing that, we can get the resolution and the benefit of e-beam directly in a one-to-one manner into the manufacturing. We have the capacity to take up any project of any size today. So if anyone out there, don't hold back. We have demonstrated not one, but 3 cameras with a unique camera architecture. And finally, demonstrated the behind-the-screen optics together with Trinamics. I think we were told to prepare a little bit the famous questions and answers here about what can we do for you. The way I see it is that meta optics is opening up a toolbox of how to design and how to work with optics. The compromise that you had to do before and the laws of what parameters you had to sacrifice in order to gain in other might not be the case any longer. I can highly recommend to work with us or any of our colleagues in the industry to discuss what is possible using meta optics, and don't get stuck on problems just because refractive optics cannot solve it. We're working with extreme compactness, polarization sensitive optics. It's extremely simple from its mechanical, what it looks like. I would say it's not necessarily simple to build it. Unique thermal stability. And what we are looking for, we are always looking for solutions and opportunities related to materials, integration, and testing. I think that's where I have my radar focused. So with that, thank you. And I don't know if we have time for questions.
Yes, thank you, Theodore. Thank you very much for your presentation. Question. So you can raise your hand through Zoom. One question for you, Theodore.
Super.
I was wondering, how do you ensure the long-term performance and stability, of your component and also the durability?
I mean, we run reliability tests and have been doing that for a long time. So all that type of testing is in-house. Many of the materials and the things we're working with, consumer electronics, we have like 1,000-hour testing, temperature cycling. We have taken many of our optics to at least 2,000 hours. It works. So we're just doing it by following ISO standards of what is required to bring this type of products to the market.
Okay, thank you. Yes, Wilfried Noyd from Focuslight. Please, Wilfried.
Hello, Theodore.
Hey, Wilfried.
First of all, congratulations. Very, very, very big news in the community that you guys could raise so much money. I have a question. How do you see it? You mentioned e-beam lithography. How do you see it? Because we saw that in other domains, like for silicon photonics, for waveguides, where steppers become more and more crucial for manufacturing. How do you see this in this community for meta optics? So once a technology becomes very interesting, the big foundries become interested as well. So how do you see this here? Or do you have to remain with nano imprint and etching, or do you see a path towards stepper-based processes?
I think it's very interesting how you even phrase the question, Wilfried, right? Because you're saying, do you have to remain like it's a bad thing, or that it would be more ideal to do stepper? We actually see it the other way around.
Okay.
We believe that this is the perfect application for nano imprint.
I see. Okay. Sorry for wording it this way.
No, it's fine. It's fine. It's completely fine, right? But it's the whole thing. Even if I had the opportunity to do it with a stepper, I would stay with where we are.
Okay.
This works beautifully.
Yeah.
We have a lot of people who have been working in other companies before, and the yields we see just right out of the bat with our technology is mind-blowing.
Okay, good. That's good for you. Thank you. Very good.
Thank you, Wilfried. And if we have no more questions, I would like to thank you again, Theodore, for your nice intervention. Thank you.
You're welcome. Thanks.
And now, next speaker, so Timos Kalos, Chief Scientist at Iron Delta Tech, and you will talk about application, especially industrial application of optical metasurfaces. So please, Timos, the floor is yours.
Yeah, thank you. Thank you for attending. I hope you can see my screen okay. I'm Timos Kalos. I'm Chief Scientist and Managing Director for Orion Delta Technologies, and I'm going to talk about the industrial applications of the metasurfaces. Now, I gave a talk about 10 years ago in a metamaterials conference in Denmark, talking about the hype cycle of metamaterials, and I introduced the concept not of the hype cycle. This is something that's well known, and I'm going to briefly summarize here for people that don't work in marketing much, but it basically plots the hype of a technology over time. And there is usually a few 5 stages. There's some kind of technology trigger that creates a spark. Then there is what's called the peak of inflated expectations on what you can do with that technology. Then this usually dies down. There is a trough of disillusionment, but things gradually pick up back again with the slope of enlightenment, and then you reach a plateau productivity, which is usually lower than the peak was. And I'm going to show you how that looked like at the time for metamaterials. Before I do that, just a couple of words about what we do. Orion Delta Technologies is a SME based in the UK. It was founded only last year. There was a team previously with Metamaterials Inc., which was a NASDAQ-listed company, over 200 people working on metamaterial applications that unfortunately had to shut down operations last year. So we've picked up some of the technology and know-how now and continuing the effort. This brings us to about 50 or more years of commercial expertise in developing and manufacturing transparent meshes, metamaterials, and in general structured functional films, which includes metasurfaces. We do more than optics in terms of the frequency range. In general, we develop optimized hardware components for various OEMs, and this include primarily building demonstrators, design, prototyping, integration, and then we work externally with manufacturing partners for volume production. I'm not going to go through all the expertise, but I just marked in red quickly to show that we're also quite good at metasurface design and fabrication. And we cover the typical like design simulation, prototyping, integration, sampling, and characterization in-house. Now, coming back to the topic of metasurfaces, 10 years ago, I presented what I thought was at the time the hype cycle for metamaterials. So what this looked like was left-handed media was the technology trigger in the 1990s with the negative refractive index. Then about 10 years later, in the mid-2000s, with the work of John Pentry and David Smith, we had the clocking and perfect lensing applications, and this did create a lot of hype and brought many researchers and interested parties in the field. Very quickly, within a few years, this died down because it was very difficult to scale up these ideas and the losses were just too large. And in 2014, I proposed that metasurfaces, which at the time were just coming around, would be the future of the metamaterial field, and this would lead us to commercial applications. So in the remaining of this talk, I would like to explore some of these commercial applications that have come with 10-year insight, and I think it's quite successful. I'm going to bring some examples from the industry, but also metasurface we've developed ourselves. Obviously, there is Metalens, I think is the most popular commercial application of optical metasurface, where they've managed to replace multiple lenses and diffractive elements with a single structure. And this is used for polarization and infrared imaging. Lumotive is also doing very good work. They've integrated metasurfaces for LiDAR, and they also include liquid crystal for some tunability. The difficulty in such products is that the metasurface metamaterial just one component, but you actually need to build the whole system to demonstrate to the end customers that this is something useful. Another example from the UK, from Kinetic, there's been a film that basically it has an infrared signature, and the purpose here is that when there are helicopters looking at chasing vehicles with an infrared camera at night, it's not easy to distinguish the police vehicles from the perpetrators. But by adding this film on the police vehicles, then at night you are able to tell which car is which. So that's a very interesting practical application. Some of the work that was done at Metamaterials that since was acquired by Authentics, this is on banknote security. The idea there was to create plasmonic metasurfaces on microsurfaces, and these produce diffraction effects, coloration and motion and other structures that are good for authenticating banknote and other security products. The benefit here is that you are able to replace the traditional micro lens with a plasmonic nanostructure, a much more compact and with much higher degree of flexibility with regards to what kind of effect you can achieve. Now moving on to stuff that we are working on currently, we have transparent metallic metasurface antennas, and one example is using these antennas as heaters and communication elements in LiDAR. The optics part of the application here is that you want to mitigate diffraction that inadvertently comes in when you try to install any kind of grating or surface in front of an optical component. So there are techniques here you can use to mitigate this diffraction so that the LiDAR sensor can operate efficiently. Another interesting application on the AR side is what we call eye box optimization. So if you look at the top right, you have a traditional reflective element on an AR glass that, as many of you know who are in the AR VR industry, is difficult to translate between different people because we have different, different eyeballs in different places and so on. So the idea here is that you use a metasurface made not out of nanoimprint, but out of a hologram. And this allows you to basically create masters that are much cheaper, and then you can create individualized masters basically at a reasonable cost so that you can mix and match each person with the reflective and optical combiner that's best for them. In combination with this technology, there is capability to integrate this inside lenses instead of on top of lenses. It's basically you can cast a lens around your optical combiner element, and this allows basically to do conventional post-processing with all the ophthalmic techniques and not have to worry that you have a very, very sensitive metasurface element that you have to protect and worry about. So that's my quick round trip of applications, and I'll close off with outlook, what I've seen in the last few years and where things are going. So a couple of points. There is definitely a shift from bulk metamaterials to surface metamaterials and metasurfaces. This is maturing, especially for infrared applications where they're a bit more forgiving in imperfections. The companies that are very successful have managed to leverage CMOS foundries. This is very important. But still the costs must reduce. As a starting point, if you're starting in this space, you need to be able to produce an element, I would say less than $1 per square centimeter in terms of surface area. I mean, there is obviously a lot of variation there, but that's roughly the order of magnitude you should be looking at. This means there are more manufacturing advancements required, and as everyone I think here agrees, especially for the visible frequency range, this is still a bit of a challenge, and I think it will remain a hot topic for the next 5 to 10 years. And just to close off where I think the innovation needs to happen, what are the issues currently with metasurfaces? Obviously, limited bandwidth is difficult to produce very wideband metasurface without many artifacts. The efficiency is still relatively low, especially in transmission modes. People tend to prefer reflective elements for that reason. The tuning still couples right now amplitude and phase. These two cannot be controlled independently very well. There is limited tuning range, especially in the phase. So ideally, you want to have very easy, 0 to 2 pi control, again, without many artifacts and with good efficiency. And I think this is because the tuning mechanisms right now, there are not that many. There are only a couple of things you can try, and some new ideas are needed there. And finally, many of these nano-imprint and other manufacturing techniques are incompatible with CMOS technology. I think the reason some of the companies have been more successful are the ones that have managed to integrate their designs and piggyback with CMOS technology that has been around for decades and has been cost optimized. So we need to find ways to tighten this integration, in my opinion. And with that, thank you for your attention, and I'm open for questions.
Thank you, Temos. Thank you very much for this interesting overview of application. Any question for Temos? Yes, we have one question from Ranjit Kumar. Ranjit, you are muted.
So hi, thanks for the talk. By the way, on slide number 20, you said that you leverage the CMOS foundry compatibility in manufacturing the metasurface, and then subsequently you said on the slide number 21 it is incompatible the CMOS step foundry. So how these two different things in the two different slides?
So both are true in the sense that there are some metasurface designs that are compatible and are being produced, but a lot more work needs to be done. And this needs to be fully integrated, I think, until the foundries scale up and bring more of this metasurface type manufacturing.
Okay. Thank you.
Yeah.
Thank you, Ranjit. Any other question? From my side, do we have any specific challenges, to integrate such component in more global systems?
Yeah, this is a very big question. We need to bring into this talk more of the CMOS foundry people, but it is possible to adapt the processes to be more compatible with metasurface manufacturing and patterning. It is expensive, and there need to be applications that drive that business model. I think we will get there, but right now is a bit slow. I think it's from both sides. You need to have the demand for application, a good revenue model, and that will justify the CapEx investment to integrate this metasurface manufacturing into CMOS.
Yeah. And from your point of view, which application could drive, this development in the next few years?
I think the ones that I mentioned right now on the infrared imaging, like cameras, they're quite good. From my experience, anything that involves the human eye, like if you have a metasurface that the eye will look through it, it's very difficult to trick. The eye picks up every little detail, attenuation, artifact. It's very, very difficult to do it in the visible. So I think infrared imaging, infrared cameras are a good starting point. Next, I would say visible cameras, and then we would move to putting these things in front of eyeballs.
Thank you, Temos. Yeah, we have another question from Ranjit. You are muted, Ranjit. Yes.
No, sorry, I think that was the previous question.
Okay, perfect. Thank you. And maybe a last question from my side, Temos. I would like to ask you, the epic question. What can you do for this community, and what could they do for you?
So what we offer is we have good commercial experience with integrating products. So people usually come to us when they've tried other solutions and it doesn't work. I often say that we're the Sherlock Holmes of light. So you have a problem and you tried conventional solution and nothing works, then you come to us. We have good experience on metasurface and metamaterial, and we can probably find a good solution.
Okay, so thank you, Timos. Thank you very much.
Thank you
for presentation. And now we can move to our next speaker. So we welcome Daniel Pereira. You are sales manager at Buller, and you will talk about optical coating on thin glass enabling manufacturing of metastructures. So Daniel, please, you can start your presentation.
Okay. Hi, can everybody hear me, see me? Is the screen okay now?
Yeah, perfect.
Yeah, okay. Thank you very much. Thank you for the opportunity of showcasing what we are working on at Buller. So today the focus will be on the vacuum equipment that we are working on, targeting the manufacturing of metastructures, and particularly thinking about thin glass coatings. Before getting into it, I will just introduce a little bit the company and the main product that we are focusing on for this talk, and then go a little bit more detail into the manufacturing side. So we are Buller Labeled Optics, and we are producers of vacuum equipment for all sorts of applications, which you can see listed here. Targeting the fields of optics, photonics, energy, ophthalmics, and so on and so forth. We provide equipment that ranges from PVD to CVD, and we aim to provide functionality of substrates, be that flexible substrates, rigid substrates, glass, silicon, any kind of substrates, giving them a functionality by an optical coating. And then within this optical coating, depending on the type of precision and complexity of the optical coating, we can discuss different applications. So simpler applications in the ophthalmic world go into more advanced applications in precision optics, and even higher in more demanding applications in the semiconductor world. So we try to cover this field of applications with our equipment, and this is definitely our wheelhouse. Today, so we also are in the customer for the customer. So we have servers all around the world where we can provide service to our existing customers and new customers. And we have 3 application centers all around the world to allow the customers also to come to us with their demands and with their challenges, and we try to fulfill the requests coming from the different markets. We have more than 3,000 systems installed worldwide, and from our turnover, we always invest 7% into innovation. And the topic that we are presenting today is just a result of this R&D and this innovation that we are working on. Today, I will focus mostly on a single product, which is called the Helios series. The Helios is a magnetron sputtering technology tool that is capable of doing optical coatings on wafers, particularly targeting, in this case, the field of semiconductor, where we do the functionalization of wafers with various optical coatings, which can range from a single layer to multi-layer structures with more than 100, 200, 300 layers. We focus on 3 or 4 main pillars with our technology and 2 different tools, depending on the wafer size that we need to coat. So a 200 millimeter or 300 millimeter wafer in diameter. And out of these 4 pillars, we focus on the technology itself. So we aim to optimize the technology for the different types of applications and the different types of products. And it's a technology that is already well proven in the market. So we have more than 200 of these systems installed worldwide. We are also going in the direction of semiconductor, and in semiconductor, particle is fundamental. So we have developed our technology to be producing the lowest level of particles possible. And we have recently reached the target of below 100 particle size, 160 nanometers or more. So this is the target for semiconductor fabrication. when we come to the filter, we aim to achieve the highest uniformity on the highest wafer size possible, and you can see here that we are achieving up to below 0.23% on a 300 millimeter wafer. And finally, we also focus on automation. So by providing solutions to manual and automated loading of wafers, which include solutions for 200 millimeter and 300 millimeter wafers. So this is just an overview of the technology and the company itself. So I don't think I need to explain this slide. Again, this has already been touched upon a couple of times during the meeting today. But the aim of the Metalens is to reduce the cost and reduce the size of the optics used in different applications. So we have emerging applications such as AR, VR, and we have also the evolution of the imaging technologies, and all of them can benefit from the reduction of these units. So Metalenses poses the promise to reduce the size and to reduce the cost of the traditional optics that are currently being used. And here, our technology, our Helios series, we believe can help the ones that are actually working in the fabrication of these structures. We have a lot of know-how that we can now pass on to the Metalens world and to the Metalens market. So we have worked on titanium oxide coatings, which was already presented today. We have extensive work on color filters, anti-reflective coatings, as I mentioned before, low particle coatings. So this is well within what we have experience on. And I've skipped the point of the thin glass because this is the focus of today. So we also aim to provide coatings on glass wafers of a certain thickness. So we'll talk about thin glass handling and thin glass coating. And why thin glass? Because again, touching upon the topic of lightweight, so the promise of the metastructures comes from the reduction of the size, which then reduces the weight of the units used in the various applications. So when we go to AR, VR, for example, lightweight is key. It's a very important point. So when we couple this to the increasing demand for cost reduction, which goes in the direction of increasing the number of products that can be used in a wafer, meaning increasing the wafer size, we see the challenge from our investigation. We see the challenge that if we increase the wafer size and we still build the traditional optics and the traditional structures on the wafers with a certain thickness, we start seeing problems arising from the type of stress that coatings can give rise to. And if you see here, what we are looking at is a wafer with a thickness of 0.21 millimeters and a diameter of 300 millimeters. So a traditional wafer size, but a much smaller thickness. When you do a coating on a wafer like this, you might expect, so a traditional coating might end up in two different results. One of them is, you see what is happening here, the wafer bends a lot. Another more problematic would be that the wafer completely breaks during the processing. So if we are going towards lightweight solutions, if we are going towards reducing the total thickness of the system, we also need to think from a manufacturing point of view how we can reduce the stress induced on glass substrates with a certain thickness and a certain diameter. And this is what we are working on. So we have spent a significant amount of time developing processes that reduce the stress induced on the wafer. And what you see here now is an optical coating. Well, basically the same optical coating as you see here on the top, but with a very, very low stress induced, which means that now we are capable of doing coatings with a certain thickness, which give rise to very little stress on the wafer, which means that they are bending less and less and less. So when we go to manufacturing of the metal lenses, this could be a good step towards producing different structures and different types of coatings on wafers with a certain size. And more importantly, because like I said before, uniformity is key. We also measured here this 1.2 micron thick AR coating. So you can see the performance here. And on the plot, we measured different points of the wafer that you are seeing here. We measured the performance on the different points across the wafer to understand if there is a variation of the optical performance. And we overlapped all the transmission plots. And when we zoom in onto a specific area, you see that within the wafer we are achieving plus minus 0.25%. So meaning we can actually coat do these thick coatings with low stress and high uniformity across a wafer size of 300 millimeter, and more importantly, a wafer thickness below what is used currently in the industry. And we have now solutions towards doing coating on thin glass, which we hope can benefit the field of metastructures. So this as a conclusion, and I hope that here I've made a little bit of a teaser of what we are working on, and now I hope I can answer the two traditional questions from EPIC. So what we can do for EPIC and for the EPIC members, and what the EPIC members can do for us. We've shown here that we can work on thin glass coatings. I didn't touch much on the topic of throughput and handling, but this is also something that we work heavily on. So we try to also increase the throughput of the production in order to optimize the number of product wafers that can be done. And we also have developed solutions for automation. So really bringing in and out the wafers from and to the fab. So we are now fully capable of doing coatings, anti-reflective coatings or functional layers, which can be used later on glass thickness of 0.21 millimeter. And so what the EPIC members can do for us. So we want to understand if this is the right approach, if we're going in the right direction. So this is where the EPIC members could really help us. And this is where basically the EPIC members then do the functionalization and the metastructure fabrication. So we hope that we can enable this manufacturing step. So this is the end of my talk. Yeah, thank you very much for your attention. And if you have any questions, I'm more than happy to answer.
Thank you, Daniel. Thank you very much for this nice presentation. Any question for Daniel? Yes, Dominique from Photonics Biz.
Hello, thank you very much for the presentation. Do you have can we have some optical measurements or refractive index on your layers and different results on that, as shown by yes?
Yes. So in terms of optical performance, we can share not in such a public forum, of course, but I can give you some hints. For example, when it comes to, I think there were some presentations about titanium oxide. So we have made publications on our titanium oxide production, and there a refractive index of 2.5, 2.51 is possible on the titanium oxide with a high level of very amorphous. So I would recommend, if you would like to know more, feel free to contact me. Also, we can share these publications with you.
Okay, thank you very much.
Yeah, you're welcome.
Thank you, Dominique. Any other question for Daniel? Okay, so if we have no more questions, thank you again, Daniel.
Yep, thank you.
For this presentation, and let's move on with the next speaker, Lieven Penning. You are a founder of Planopsim, and you will talk about your Metalens design software. So please, Lieven, the floor is yours.
Yes, thank you for the introduction. I hope you can see my screen. Indeed, I will talk about, we've already covered a lot of the fabrication aspects. I would now like to talk a little bit about design, because that is what we specialize in at Planopsim, to make the design of metasurfaces as easy as possible for engineers and scientists. We do this through our design software that we have brought on the market since 2021, and also through design services that we do for various companies and research institutes. And our tool scale, when you want to design a metasurface and integrate it into an application, you need to design from the nanoscale pillars over to large area components and then integrate these into a system. And these are actually the different design skills that we also incorporate into our tools. So our team can support, in fact, the whole workflow through our software and our services from the very initial step. So we've seen here refractive optics, diffractive optics. And the first question that a designer always has to ask is, well, what type of physical mechanisms, what kind of optics do I need to use to solve these problems? Metasurface is not the solution for every problem, but it does give a lot of new design options. So in this concept stage, we are already supporting our users. Then we go on to model systems. This is traditionally done in ray tracing because there are that many free variables that the only way that you can really model a system is through ray tracing. But we inform the ray tracing with the capabilities of the nanostructures that come from our full wave solver. And then we use these libraries of structures, integrate them into full components, which can go up to the centimeter scale. We validate that and we integrate that to fabrication as well. I will show a couple of examples of this in the next series of slides, but the rapid iteration through these various steps is very important if you want to take something from a nice academic curiosum to a real product, and that's why we support this as close as we can. The first step is always to design the nanostructure. So this is sub-wavelength scale, so we need full wave Maxwell solvers for this. Anyone that has done Maxwell solutions knows that it's very time consuming, but it is very accurate. And we in our software use the RCWA algorithm. Other people use FEM or FDTD. The bottleneck remains the same actually in this case, that you need to calculate these whole structures. The results are the same. We pick RCWA because it's generally faster than the other methods. The main question that you have here in the design is what should the structures look like in order to reach the performance that I want? This is typically phase and amplitude control, but could also be polarization control, for instance. We implement for this various types of algorithms to help you optimize that. So you see here a benchmark of 7 different parts. We find that particle swarm and covariance matrix, for instance, as well as Bayesian optimization, tend to work really well, both on reference problems as on actual problems. But all of these are a designer choice that has to be made while they are designing, and we allow that, of course. So here you see typical, let's say the Pancharatnam-Berry type design that is seen in a lot of papers. It's not so practically useful, but it's a good reference problem. And then once we have our library of nanostructures, of course, we want to go on and make functional components like lenses out of that. Then we go on to the component design. For instance, here we have a small lens that we've generated as a demonstration. So what you do as a designer is you identify through ray tracing or through theory what's the required lens profile, the wavefront that you want, and you map that back to the different structures that you have available that can be manufactured. Then you calculate what should the shape look like, what's the GDS, what's the projected phase function, and what's the final efficiency point spread function, and so on and so forth. So all of that is then calculated. In this example here, we're just using titanium dioxide pillars, but it's completely up to a designer, of course, which structures to use. And some of the speakers here have already covered that it's generally a good idea to have high refractive index contrast. That's why we're looking at these dielectrics for this type of design. And once you have your design, you can have it manufactured. So we produce the GDS file directly. This is an example that was created by one of our customers. So they use the software to generate this IFTA phase-only hologram meant to project an image onto the asphalt. The GDS rolls out and is fabricated. Here you see an SEM image and performs as a very compact projection optic that is then used and measured and was up to 70% efficient. That doesn't sound like a lot, but if you use a conventional projector, those are actually only 10% efficient. So this is a very nice step up from that. For practical applications, we need large sizes of design. And if you look at conventional methods of designing this, especially the full wave simulations, they are typically restricted to at most 100 microns or something of that area. By using multi-scale simulations, we are actually able to design much larger areas in a practical time frame. So we go up to 10-15 millimeter is the current design limit of our servers that we use, and this can still be done in reasonable times of almost 2 hours, but still in good time. So we can go 22,000 times larger than what you can do in full wave, and we can do this in short times so that we can iterate rapidly through different designs. We can also apply different methods to have more accurate calculations of the nanostructure's behavior. So some of you that have a bit experience with this know that often people rely on using the pillar as if it's surrounded by all the same structures, where in reality they are different structures. This is called the local periodic approximation. It's a very fast way of calculating, but it comes with known limitations, especially if we go to high numerical aperture lenses, for instance. If we use an overlapping domain analysis that also takes into account the surrounding pillars, we can still calculate rapidly because we are working on subsections of the lens and iterate through the whole lens. We can calculate large areas without having to full wave calculate them, which would blow up any high performance computers' memory limits. So we can still do this in this way. And then we can go on to fabricate these metasurfaces. So if you don't have your own fabricators, the photonics world has since a long time known the concept of PDKs, process development kits. Since 2023, manufacturers are offering established PDKs for supported wavelengths of 940 and 532 nanometer directly as a way to design. So as a designer, you actually don't need to worry about which structure specifically to use. You can select the corresponding vendor's PDKs, run the design for your target wavefront, and then go through the design and send that straight to the manufacturer. So this is another aspect of rapid prototyping, rapid iteration that is developing and a sign of growing maturity for the metasurface market. We can also establish the fabrication effects through Monte Carlo simulations of fabricating a metasurface. So if we have a nominal design and we then start to randomly introduce errors into that fabrication process, as will happen in reality, the simulation allows to estimate the effects of that. And this distribution plot that you see here, in fact, contains 25,000 different lenses that were simulated in different ensembles. This is something that's only possible, again, through the application of multi-scale simulations. So that's fine. We can make fabricatable single components. We can also then integrate that into systems through plugins to ray tracing solutions. So the color router was already mentioned earlier today as an example. What we have shown here is that a designer can first design its lens system and then through a DLL plugin import the specific behavior of the metasurface into the refractive ray tracer and use their elements of the metasurface design, which are precisely the ones that you couldn't reach using refractive optics, such as this multiplexed wavefront color router here. So we see the blue wavelength is focused on the blue subpixel, the red wavelength is focused on the red subpixel. We have this nice color splitting that you wouldn't see with a conventional optical lens. All of this is directly available and used by many of our users. I've talked a lot today about design, and I would like to wrap up here with stating that when we think about bringing a technology to market, we don't just need design, and a design tool is not just something that's used by a designer, but in fact, the whole ecosystem has to develop, and I think Metasurfaces is coming along very nicely here. And there is Planopsim's role specifically. So we can offer to the ecosystem design solutions and expertise to make sure that your products are fully integrated and well designed. And we are looking for partnership with all of you to improve the accessibility of meta and nano optics all over the world, to improve design for manufacturing, and to develop the high performance simulation tools needed to make this as fast and efficient as possible. Thank you very much.
Thank you very much, Lieven, for your presentation. Any question regarding design? Yes, Hakan Alabos from Photonics University, please.
Thank you. Thank you very much for this nice presentation. I'm wondering about this local periodic approach that you mentioned in your presentation. So usually when we talk about this meta design, we are talking about periodic surfaces, but as you mentioned in your presentation, there can be some instances that we have using different non-periodic structures and huge areas. So my question is, what are we talking about when we talk about this local periodic approach? What is the size of these local periodic structures? And the second question is, even with local periodicity, we will encounter with some intermediate sections between two local periodicity, and how the simulation can handle these intermediate sections.
Yes, thanks. That's a very interesting topic, and I think I don't have time to go into all the details here, but I propose to follow up over email about this. But I will briefly clarify that usually, and this is a method that was traditionally used, and you find it back in a lot of papers, the local periodicity is applied on the level of a single nanostructure, what they call a meta-atom. So this is in itself smaller than a single wavelength to suppress diffraction coming from it. So this area is quite small, typically 500, maybe 300 nanometer in unit cell size. And that's the periodicity used in the local periodic approximation. This approximation breaks down when the pillars surrounding the meta-atom are very different in size from the pillar itself. And so you get there what they call near field interactions. So interactions between a pillar and its neighbors. The overlapping domain analysis calculates areas, including those neighbors, to still know the response of the meta-atom surrounded by its neighbors. And then you scan through, but you keep the surfaces overlapping so that you mitigate this boundary effect that you just talked about. So if we would just patch side by side different simulation areas, that would indeed introduce additional approximations there.
Okay, thank you very much. Yeah.
Thank you, Hakan, for your question. And yes, thank you again, Lieven, for your nice presentation again to one of our meeting. Thanks. And now, last but not least, speaker of the day. So we welcome Matthew George from Moxtech. So Matthew, you are application scientist, and we'll talk about progress in commercialization, visible wavelengths, metalenses. So Matthew, the floor is yours. You can start your presentation.
Okay, thank you. Can you guys see the screen?
Yes.
Okay, very good. So the purpose of this talk is to share Moxtech progress in commercializing visible wavelength metalenses using our nano-imprint lithography and etching-based approach, similar to some of the capabilities that NILT already discussed. But if you have any meta-optic development projects that require a path to high-volume manufacturing, we'd be interested in discussing the opportunity. Let's see if I can advance the slide. Let me try to escape here. Can you still see the screen?
Yes, we can see your screen.
Okay. I'm not able to advance the slide right now.
No.
Oh, there we go. Okay. Apologize for that. So yeah, Moxtech was founded 39 years ago in Utah. We have about 250 employees working on X-ray technology components and also optical nanostructures. On the optics side of the company, we've been manufacturing nanostructures for 25 years, and we offer a complete high-volume manufacturing solution, including optical nanostructure design. So the MOXTech fabs, they're all located in Orem, Utah, south of Salt Lake City. We have 8 buildings with plentiful clean room space for high-volume manufacturing. So our optics products include wire grid polarizers. We've been the market leader for a couple decades, and also include pixelated versions for polarization imaging applications, as well as various polarizing beam splitters, and more recently, patterned dielectric nanostructures, including wafer scale meta optics. So we have solutions spanning wavelengths from the deep UV to the long wavelength infrared, and we have excellent durability due to all inorganic nanostructures. MOXTech capabilities are listed here. Really what sets us apart are our various nanoscale lithographic capabilities, including nano-imprint lithography, and also our etching capabilities. We have demonstration scale and production scale mastering processes ready for your application, so we can help you to verify and optimize a series of designs and then scale to production with a high volume master. So MOXTech Metalens designs or meta-optic designs have certain manufacturing limitations, which are currently listed here. We can make both visible and near-infrared metalenses, and we offer several options, including reflective or absorptive front side and backside apertures, integrated color filters, and also protective overcoat, which I'll show here. This is an example of our etched high aspect ratio pillars. So the aspect ratios can reach up to 15:1. So these are fairly delicate, but after hard mask removal, these structures can then be overcoated to protect against handling damage as shown here. So without overcoat, even the paintbrush can damage the Metalens surface, but with overcoat, there was no damage. And the overcoat can also act as an anti-reflective layer and boost transmission significantly. So others have discussed that Metalens could also be infilled with a low index material, but the advantage of our overcoat is it spans over the top of the pillars, maintaining the high index contrast between air and the high refractive index material, and maintaining reasonable aspect ratio requirements. So late in 2023, we installed a wafer scale metrology tool for MTF, focusing efficiency, and other meta-optic measurements. And this was an early result for a small 200 micron diameter Metalens before full process optimization. And we saw that these smallest diameter Metalenses have improved MTF performance near the diffraction limit, which makes sense since chromatic aberrations scale with lens diameter. Chromatic aberrations, of course, also scale with the source or filter bandwidth on your metrology tool. And these measurements didn't even utilize a particularly narrow bandwidth, which makes the measured MTF performance all the more impressive. So this result demonstrates the promising potential for applications utilizing small diameter metalenses. We've also created methods to measure absolute focusing efficiency using this tool, and we've demonstrated greater than 90% absolute focusing efficiency for 1 millimeter diameter 0.2 NA lenses. Larger diameter lenses have more aberrations. Despite this fact, we decided to measure a 4 millimeter diameter conventional plano convex singlet lens from Edmund Optics and compare that to the performance of our red and green metalenses with the same diameter and focal length. And even though our metalenses would show better performance with an improved filter bandwidth on the metrology tool, it's important to show an apples-to-apples comparison to a traditional lens utilizing the bandwidth requirements of the end user's applications. Perhaps surprisingly, these MOXTech visible metalenses show better MTF contrast than the simple singlet. So overall, this is a very encouraging result. Again, these reported MTF values here are maybe lower than one might expect because these are large diameter metalenses and the source bandwidth is fairly large for this type of hyperbolic metalens design. So 2 years ago now, we went ahead and built an iPhone metalens assembly with one of our green metalenses. And here's a schematic of the setup. We aren't camera designers, as Theodore mentioned, that's quite challenging. So essentially, we just slapped our Metalens on top of the iPhone camera and used it as a simple macro lens for magnification of small features. Here are color images that we captured of a foreign banknote and the cross-section of a pumpkin stem. So to our knowledge, these were the first high-quality visible metalenses made using production scale processing, and demonstrate that reasonable image quality can be achieved when using metalenses, even with traditional RGB filtered sensor. So MOXTEC's built metalenses in a variety of different diameters, ranging from 200 microns to 10 millimeter diameter, and we have the ability to go up to 1-inch diameter. We've designed metalenses with various operating wavelengths, from the violet to the mid-wave infrared. We could do long-wave infrared as well. And we've designed them at various focal lengths shown here. Currently, it's difficult for businesses to explore the possibility of incorporating metalenses into their optical systems because metalenses are generally available on a custom order basis only. So to make this kind of evaluation easier, MOXTEC is making visible and eventually near IR metalenses available off the shelf for benchtop and integration testing. So these circled samples are what we're initially offering, and other options should be available later this year. So I'd like to briefly discuss some new and hopefully exciting MOXTEC capabilities, including nano stacking of optical filter components at the nano or micro scale. So traditionally, when multiple optical filters are bonded together, they can become quite thick, especially when multiple substrates are involved. Utilizing our overcoat technology, we can stack various filters on a single substrate at the nano scale, including wire grid polarizers, wave plates, meta optics, color filters, and so forth. So here's a simple example where we've built a Metalens on top of a wire grid polarizer. On the right, here's another example of a multi-stack. So metalenses on both sides with overcoat layers, color filter, and absorptive apertures, all on a single substrate built at the wafer scale. Furthermore, this was actually an off-axis imaging metalens for eye tracking applications. In this case, the requirements were given by MOXTEC, provided to ANSYS, and the meta-optic design and optical modeling was completed by ANSYS. And then partnering with our NIL tool vendor Skill, we built this stack, a double-sided Metalens stack. But actually, the images shown here were from a slightly different stack where all the imaging functionality was combined into one metasurface layer on a single metasurface. So we built this kind of assembly here. And on the right is the comparison between the ANSYS modeled and MOXTEC measured images of an eye. So this kind of design, off-axis design, allows some added flexibility in terms of eye tracker placement. And it also gets rid of most of the zero-order leakage issues. So we hope this demonstration of a complete meta-optic design and manufacturing workflow will eventually lead to a PDK or meta-atom library for ZMAX. But if you don't want to wait for that, I would encourage you to contact PlanOpSim, who just presented, and use the visible PDK that we've already released, which we announced at Photonics West. We plan to further develop modeling capabilities of our meta-optics foundry processes with PlanOpSim in the future. Finally, we also can vary different filters or stacked nanostructures or meta-optic devices on a pixel-by-pixel basis with applications in imaging polarimetry or hyperspectral imaging, for example. Please let us know if you're interested in any of these concepts or capabilities. With that, here are my conclusions and some areas for future work. I'd like to emphasize that MOXTEC already has several operational fabs, and we can scale the high-volume manufacturing quite simply using our foundry processes. I should also mention that we've been working recently with Synopsys on manufacturing aware near-infrared Metalens designs based on the MOXTEC foundry processes, and initial results are encouraging. Again, if you have any meta-optic development projects that require a path to high-volume manufacturing, we'd be interested in discussing the opportunity. Thanks for your time, and I'd be happy to answer any questions that you might have.
Thank you. Thank you very much, Matthew, for your presentation. And any question for Matthew? I was wondering, Matthew, how do you tackle, the challenge of scaling up the production while when you want to maintain the nanoscale precision and reduce the production cost? How do you tackle these kind of challenges?
Yeah, we use basically a nano imprint lithography approach. So all the lithography is done on a master level, all the fine scale lithography, and then we can make many, hundreds, if not thousands, of stamps from an existing master, and then we can print hundreds of wafers per stamp. So you can get tens of thousands of wafers per master. We can, I think our fabs can do over 100,000 wafers per year of optical nanostructures. And with our nano imprint tool, we can probably do 30, 40,000 wafers a year. And we could, of course, get more tools. The metrology, on the other hand, we might, if we're talking about small lenses where you have thousands of lenses per wafer, we'd probably need to get additional tools. But we're ready with all of our tool set is 200 millimeter diameter wafer fab based. So we can manufacture many tens of thousands or hundreds of thousands of wafers fairly easily with our tool set.
Okay, great. Yes, we have a question from Wilfried. Focus light.
Very impressive again to see how far Meta has come. This PDK was mentioned now a couple of times. Does the PDK include the optical limits of what is feasible? So when I want to design something and then transfer the PDK, does the PDK then tell me, oh, this is not possible? Or I usually want it the other way around, that the PDK tells me what are my design limitations in my design process. Is this available already?
Yeah, the PDK or MetaAtom library is based on our foundry processes and design requirements. So it's already built in. Basically, you just get like you'll have a list of different MetaAtom, either diameters or just a pick list with different phase response. And so you can map your required phase shifts to
I see.
the MetaAtom library that we've provided.
Okay. Good. Thank you.
Thank you, Wilfried, for the question. And one question from Olaf van Ofsten from Eclipse Optics. Please, Olaf.
Yes, thank you, and thank you for the presentation. I was just curious about these off-the-shelf lenses. Are those like do they have a spherical phase, or how are they designed? Like a spherical lens.
It's like they're like an A-sphere hyperbolic phase profile. I have a slide somewhere in this deck if you want to go over the details, but yeah, there's more information on our website.
Okay, cool.
Off-the-shelf offerings.
But the lens that you had the MTF test of, where you compared it to the conventional, that was like a spherical.
Yeah, more like an A-sphere. Yeah.
Okay, that was A-sphere. Okay, nice. Thank you.
Thank you, Olaf. Another question from Nicolas Etler, Advanced Micro-Optics Technologies. Please, Nicolas.
Thank you. Hi, Matthew. You mentioned on your future roadmap to look closer into metalens arrays. Can you elaborate a little bit more on that, please?
Well, we're under NDA, but there's various illumination applications that might be well suited for metalens, metalens arrays, and then someone previously showed an example. Oh yeah, the first speaker where you can do, I guess Samsung, you could do kind of color sorting applications as well, or polarization based imaging like Metalens with the Z. So yeah, there's various applications that could be on the sensor array or on the micro LED type array or something of that nature. So.
Okay, thank you.
Thank you, Nicholas. Another question, Olaf? Or...
no, sorry.
Okay. Okay, no problem. And I saw maybe Jorge, you had your...
Yeah.
Yes.
Thank you for your presentation. Very interesting. Just a general question, perhaps not only for you in the audience. It's just sharing my mind. It's how do you feel the market for this niche, for these technologies? You have indicated bank security notes. In a time where Bitcoin, credit cards seems to be predominating in this market, which should be the future for this very specific niche?
Yeah, that was just kind of an example of visible Metalens imaging capabilities, just combining Metalens with standard lens.
Just to share opinion, because we have customers in this. Just to share opinions.
Okay. Yeah. The banknotes. I guess there's been some interest in security features and so forth. So yeah, I see that as a potential application, but like you said, people have moved towards digital forms of currency. So it's kind of debatable about long term how that's going to play out.
Okay, thank you.
Thank you, Jorge. And if we are no more questions, I would like to thank you again, Matthew, for your presentation. And before to let you leave, I would like to share my screen again and highlight, these two events. So one physical event, which will be organized at Thales in France, in Palaiseau, and we will talk about disruptive optics. And we'll also cover the metasurfaces, metalenses topics. And also the 2nd of April, we'll have this market report on metamaterials and metasurfaces for optics and radio frequencies. It will be presented by Thematis. So I warmly invite you to join these two meetings, of course, if you can, because it will be interesting for you, for sure. So thank you very much to all of the attendees today, the speakers as well. We really hope that you find this meeting relevant, and wish you a great afternoon and a great evening or a great day, depending on where you are in the world. So thank you again.
Thank you very much. Bye.
Thank you.
Bye.
Thank you. Bye-bye. Thank you.
Thank you. Bye.
Thank you. Goodbye.